Okay, guys, so we're going to have a look at the reaction of alcohols here. We're going to start by looking at the various types of alcohols you can get. Now, this 1 degree, 2 degree, 3 degree symbol indicates a primary, a secondary, and a tertiary alcohol. You can subdivide alcohols into these three classes. So a primary alcohol would be where um, essentially one carbon atom is bonded to the OH group. So the simplest primary alcohol would be something like methanol. Alternatively, you could get methanol. Alternatively, we could have ethanol also as an example of a primary alcohol. Again, just one carbon. The carbon that's bonded to the H group has just got one carbon coming off it. In this case, obviously with methanol, there are no carbons coming off it. You can't get any simpler than that. But ethanol is also a primary alcohol. So in a secondary alcohol, essentially the carbon bonded to the OH is a CH. So simplest example I can think of, which would be, squeeze it in here if I can, propan 2-ol. So if you can see that, propan 2-ol, that would be classed as a secondary alcohol because the carbon bonded to the OH is a CH. Alternatively, you could think about it in terms of, oh, the carbon bonded to the OH has got two carbons coming off it. Another one, a secondary alcohol, might be something like, if we just add one extra carbon onto there, still a CH there, no CH2, CH3. So here we'd be looking at methane eth probutan 2-ol. So a tertiary alcohol would be where the OH is bonded to a carbon where there are no hydrogens on that carbon. So, I'm squeezing this in here. So, so if you imagine the COH like this, then that might be a CH3. I have another CH3 down here and another CH3 here. And if you look at that structure, that would be 2-methyl propan 2-ol. Okay. Right then, guys. So, primary, secondary, tertiary alcohols. You can't get a quaternary alcohol because you can't have any less than one, than this carbon with no hydrogens, can you? You can't have any more than 3 other carbons bonded to that carbon if there's an OH bonded to it too. Right, so if we start looking at some reactions of these alcohols then, so first of all, a way of making alcohols. So industrially speaking, ethanol, probably the most common industrial alcohol, is manufactured industrially by taking ethene and adding water across it. So this is an addition reaction. Came across some addition reactions of the alkenes when we looked at that poster, remember? So here we're going to add water across our double bond here, and that's going to give you basically one product, which is ethanol. So if we imagine, here's our water. So there's the OH from water, sorry, the H from water rather, and there's the OH from water. And that's our alkene here is there, but obviously the double bond is gone. So this process carried out at quite forceful conditions, 300 degrees C, 60 atmospheres pressure, so everything's squished together. You've got a phosphoric acid catalyst here, but even so, under those forceful conditions, only 5% of the ethene is converted into ethanol on each pass. But by removing the ethanol from the equilibrium mixture and recycling the ethene, it's possible to achieve an overall 95% conversion. So that's how ethanol is made industrially. That's for use in the chemical industry mainly. Ethanol obviously is found also in terms of alcohol for drinking purposes, and for this purpose it's mainly produced through fermentation. So the starting point for fermentation is a starchy plant such as maize or wheat or barley or potato, depending on what you have at hand. First step is to break the complex carbs into simple ones. So that means heating the plant in hot water, and then you add yeast. Now that needs to be at about 35 degrees. If it's any hotter or any colder, the yeast won't work so well, and fermentation will occur. So the air is kept out of the mixture, otherwise you'll end up with vinegar and it doesn't taste so good. So the reaction here, we're going to make ethanol, C2H5OH, that's the product that we're after. You also make CO2, so you need to release that CO2. And so in terms of balancing here, so we've got 6 carbons in our carbohydrates from our potato or maize or barley or whatever, and we need to balance those 6 carbons. So the way this is done is that we get 2 of these, and that means up to 4 carbons there, so we need another 2 CO2. So hopefully that's all balanced now. So if we check, 4 oxygens here, but another 2 there, so that brings us up to 6 oxygens. 6 hydrogens here rather, but that is all doubled, so we're up to 12 hydrogens there and 12 hydrogens there also. Yeast is killed by ethanol at concentrations in excess of 15%. So effectively, once the mixture has produced 15% ethanol, then the yeast gets killed away. So you can't really make the mixture any stronger than that from the yeast mix. If you want to have a drink that's stronger than 15%, then you might want to think about distilling the mixture to give you a stronger drink. And you can get up to 96% alcohol by that distillation process. Okay, so effectively this reaction here then is essentially the reverse of this one. Okay, so this is a way of going from an alcohol to an alkene. So it's a simple way of making gaseous alkenes like ethene. So if ethanol vapor is passed over heated aluminium oxide powder, the ethanol is essentially cracked to give ethene. So mention the word cracked there rather, because this is very similar to the process that we do at GCSE, where we crack crude oil, we crack the longer hydrocarbons in crude oil to give us alkenes. So essentially what we're going to do here is going to form an alkene, and in this case it's going to be ethene. And obviously you'll end up forming H2O as well, because you've driven that water off. So if you imagine in this one, you have the H, the OH there, and there's a H2O there. Okay, so the process can also be made to work by heating with either concentrated sulfuric acid or concentrated phosphoric acid. Concentrated sulfuric acid particularly good at absorbing water out of various compounds. Right, so that's that half the poster covered. Now onto this half now. Now this particular section of the poster comes up again and again and again, and so I'm going to take a bit of time to try and go through this as clearly as I can. So oxidation of primary alcohols. So we can oxidize alcohols to give us a variety of products. So first product that you can get if you do a mild oxidation is to form an aldehyde. Now aldehydes have got essentially C double bond O and a H, that's their grouping. And in this case, we started with 2 carbons, so we're still going to have 2 carbons. So there's our product, and that is called ethanol. Ethanol. And you can make that by mild oxidation of ethanol. So the oxidation, we use this orange potassium dichromate in acid. Always has to be in acid. The O there is just in showing you that oxidation is taking place, and the primary alcohol is oxidized to give you this ethanol. Oxidation here you can think of in terms of, if you imagine we've essentially lost these 2 hydrogen atoms, haven't we? So you can imagine in terms of loss of hydrogen here, the potassium dichromate in itself will be reduced in this process. If this is oxidation, then this has to be reduction, and it gets reduced to chromium 3. Now, I don't know if you remember your oxidation numbers, but the chromium here is in an oxidation state of +6. Now, if you don't know if you remember that, let's have a quick look at that. So Cr2O7, 2 minus. So if you think the whole thing has to equal -2 in terms of oxidation states, the oxygens, each one will be -2, but that's 7 of them, so give us -14. So therefore the chromiums, if you balance this sum out, needs to come to +12. But there are 2 of them, so individually they reach in a +6 oxidation state. So that effectively goes from a +6 oxidation state, use my Roman numerals here, to a +3 oxidation state, and that indicates reduction has taken place. Okay, so how do we do this? Excess alcohol is heated gently with acidified potassium dichromate, and we can remove the aldehyde by distillation as it's formed. I'll talk a little bit more about that in a minute. So, we can also go from a primary alcohol like ethanol to a carboxylic acid, and maybe you know what carboxylic acid looks like. It's got a C double bond O grouping, but this time instead of just having a H over here, we have an OH, so it's more oxidized than an aldehyde look. And we have our carbon here again, because we started with 2 carbons. We need to end with 2 carbons. And if you look at this step, this is twice as oxidized. We've taken the 2 hydrogens away, but we've also introduced another oxygen as well. So here then need more forceful conditions for this to happen. The alcohol is heated with an excess of potassium dichromate under reflux. When the reaction is complete, carboxylic acid is removed by distillation. So let's just talk about those 2 conditions a little bit. So if we want to form our aldehyde, I'm going to do a really rubbish drawing here, so forgive me on this. We're going to have our reaction mixture in the flask, and we're going to distill. So a distillation setup would look a bit like this. You would fit a condenser on here. And you'd have a container of some sort there. And probably have a thermometer or something here as well. So you'd heat up here. Now, primary alcohols, boiling point relatively high, I think it's about 78 degrees Celsius. That's because they have OH groups which can hydrogen bond. Aldehydes, however, boiling point's much lower because that OH group isn't there anymore. They can't hydrogen bond with each other, so their boiling point is significantly lower. I can't remember what exactly it is now, but it's significantly lower. So what we're saying here is, if you can manage the heat carefully, when your aldehyde starts evaporating, it'll evaporate before the alcohol once it's formed, and so it'll move into the condenser here and run down, and you'll trap it in here. Whereas your alcohol, which is at a higher boiling point, stays in there. So you can eventually get all the alcohol to be converted to an aldehyde. However, if you were wanting to do this, you would get rid of the still head and connect the condenser straight to the flask, and you would just boil it and boil it and boil it. So you have your alcohol in there and your oxidizing agent, obviously, and you would just keep on heating that, and you would get this boiling, condensing business going on, and you just keep on heating it. An aldehyde is formed initially, but that then, there's no escape for it this time. It's got to stay in there, and it'll keep being heated in with the oxidizing agent, and that will eventually cause it to form the carboxylic acid. So that's much more forceful. Okay, both these reactions, our potassium dichromate goes from a +6 oxidation state to a +3 oxidation state, and we can actually see that happening. It'll change color from an orange to a green color. It's like a bluey green. There's no color change here. This is colorless, this is colorless, this is colorless, this is colorless. You won't really see anything happening with the organic part of the reaction, but the inorganic part gives us the clue that something's going on, that orange to green color change. Now this comes up all the time in various sections of the Unit 2 course. Okay, we can also oxidize secondary alcohols. So we said our primary alcohols was something like ethanol. Secondary alcohol, the simplest I can think of, would be propan-2-ol. And so we can oxidize this as well with our potassium dichromate again, going from a +6 oxidation state to a +3 oxidation state. Gets reduced itself, but it can oxidize our secondary alcohol. And this time, the OH group here gets converted to a double bond O again here. But that double bond O, C double bond O, known as a carbonyl grouping, is in the middle of a carbon chain here. And we call these ketones, where the C double bond O is like a sandwich between two carbons. We've got a C double bond O with a H on one end and a carbon on the other, aldehyde. C double bond O with an OH on one end and a carbon on the other, carboxylic acid. But if it's a C double bond O with both carbons on either side, that's known as a ketone. And we can get a ketone when we oxidize a secondary alcohol. So secondary alcohols can be oxidized by refluxing using acidified potassium dichromate. Now you don't have to worry here about any other product being formed. A ketone will be the only product. With a primary alcohol, you can either make an aldehyde or you can make a carboxylic acid. I suppose I should name these, shouldn't I? That's ethanoic acid. And that is propanone. That would be called. Ketones end in O-N-E. Propanone. Okay, last bit on this poster then. Can't say I'm a massive fan of this particular test, but it's in our syllabus, so we need to know about it. Effectively, you can think of this orange to green color change as a test for a primary or secondary alcohol, because if you add potassium dichromate to either a primary alcohol or a secondary alcohol, we should get oxidation to either aldehyde or carboxylic acid for the primary alcohol or a ketone for a secondary alcohol. But either way, you will see this orange to green color change. So the start of the test, we'd have it as being orange, and that would be our Cr2O7 2-, our potassium dichromate in acid at the start of the test. But once the test has been completed, once we've added our either primary or secondary alcohol, that would cause the potassium dichromate to become this sort of bluey green. And that's the chromium 3+ ion that's causing that color. Describe how we test for primary and secondary alcohols and explain what constitutes a positive test. So the alcohol, a known alcohol I suppose, isn't it? Either primary or secondary. Primary or secondary is added to potassium dichromate. You might wonder, well, where's the potassium? Well, it's the counter ion to this, so we don't tend to draw it in really. It's just a spectator ion. It plays no part in any reaction, so we tend to ignore it. You can get sodium dichromate as well. Potassium dichromate tends to be the most common though. So the alcohol is added, so potassium dichromate in acid. And heated. In fact, to be honest, you don't really always need to heat it, even you can sometimes see the colour change straight away. But if you add a bit of heat, it always happens faster. A positive test is seen by orange to green colour change. Squeeze that in. There we go. So it's effectively this reaction that's going on, and we can use it as a test. If we think something's a positive or a primary or a secondary alcohol, pop it in with some potassium dichromate. If you get that orange to green colour change, then you may well have a primary or a secondary alcohol there. Can't say I'm as a massive fan of the test, because if you had an aldehyde, for instance, that would actually work as well to give you this test, but never mind, that's just my prejudice. If you put that in an exam and you write down you can use potassium dichromate as a test for primary or secondary alcohols, then you will get the marks. So that is the reaction of alcohols in 22 minutes.